Hello everyone, and thank you for taking the time to watch this presentation. My name is Tokir, and today I will be talking about my research on the evaluation of water surface elevation using the SWOT mission in the Indus Basin. This presentation was originally intended to be delivered in person at IGARSS 2025 conference. However, due to unforeseen circumstances, I am sharing my work with you in the form of this recorded presentation. The focus of my study is to assess how the recently launched SWOT mission can be used to measure water surface elevation across the Indus Basin. Here is a quick overview of what I will cover in this presentation. I will start with the introduction and followed by a brief overview of satellite radar altimetry and SWOT mission. Then I will explain the methodology and will present the results. And lastly, I will conclude with final thoughts. Let's begin with the introduction part. The Indus River supports the source of livelihood for millions of people, but this river faces growing threats from flood and drought due to the current climate change. Traditional river monitoring gauges are limited to a few sites and often vulnerable to damage during flood conditions, and hence making satellite radar altimetry a reliable alternative. Satellite radar altimetry technology began with the launch of CSAT satellite in 1978. Since then, it has significantly evolved and become a powerful tool for monitoring surface water from space. One of its important contributions is its ability to accurately measure water surface. Over here, I will explain the basic principle of this technology. As when the satellite is in space, the distance between satellite and the reference surface ellipsoid is predefined, and this distance is referred as altitude. And then the satellite in space emits a series of pulses toward the Earth's surface and measure the value of range by tracking the time delay between emission and reception of satellite pulse. And in this way, by incorporating a geoidal model and atmospheric correction, the water elevation are determined. So, building on the technology of satellite radar altimetry foundation, the SWOT satellite offers new opportunities. The SWOT mission was launched on December 2022, and it marks a major breakthrough in satellite radar altimetry. Unlike previous altimeters that provide point-based measurement along narrow track, SWOT uses wide swath radar interferometry. This allows it to observe water bodies in high resolution and on a global scale. Now let's talk a bit about the study area of this research. The Indus River is the focus of this research. Over here in this map, the blue line represents the river Indus. It is a transboundary river that originates in China, flow through India and enters into Pakistan in the Gilgit-Baltistan and Kashmir region. For this study, I selected 3 virtual stations in Sindh province, including Guddu, Sukkur and Kotri Barrages. While SWOT's find spatial resolution allows monitoring at many locations, but I focused only on those sites where in-situ water level data were available. Now let's move on to the methodology used in this research. This slide shows the overall research approach that I have followed. The main data source was the SWOT satellite, which we used to estimate water surface elevation. At the same time, we collected in-situ water level data from selected barrages. Both datasets were compared to check how accurately the SWOT results were. We also used IT database, which provides water level data from other satellites like Sentinel-3, Geoscience, and so on. All these sources were used together for validation, and the result helped us to understand water surface elevation dynamics along the river Indus. In this slide, I will discuss the step taken to prepare and process these data sets in more detail. The in-situ data were available in feet with reference to mean sea level, while SWOT data were in meter with reference to WGS 84. So unit and reference conversion were required over here. The SWOT data were accessed through SWOT River database, which provide pre-processed water surface measurement for global river reaches. I also retrieved data from DIT database, which compiles altimetry-based water level time series from various satellites. All these datasets were carefully sorted, aligned, and compared. Finally, statistical analysis were conducted to validate the accuracy of SWOT-derived water surface elevation using both in-situ and DIT data. In the result and discussion section, I will present the outcome of this study. This slide presents the water level comparison at two key locations, Guddu and Kotri Barrage. Both plot on the screen. The x-axis shows the observation dates, while the y-axis shows the water surface elevation in meter. The green line represents water level derived from SWOT satellite, and the red segmented line shows the corresponding in-situ measurements. As you can see, the SWOT-derived values closely follow the trend of the in-situ data, capturing both seasonal variation and daily fluctuations quite well. This indicates a strong agreement between satellite and ground observation, especially at Kotri Barrage, where the alignment is visually tighter. This slide shows the water level comparison at Sukkur Barrage. Similar to the previous plot, the x-axis and the y-axis represent the same values. Here in this plot, the additional blue line corresponds to DIT satellite-based water level. Among the three stations, Sukkur is the only location where DIT data were available. As shown in the plot, all the three data sets follows a similar trends. This strengthens our confidence in using SWOT data to monitor river water levels, especially in data-scarce region. This slide summarizes the statistical performance of SWOT-derived water surface elevation against in-situ data for all the three barrages. Looking at the first table, table number 1, which represents the statistical analysis for Guddu, Sukkur, and Kotri Barrage between SWOT and in-situ water levels. The correlation is very strong, which indicates excellent agreement. The root mean square error and mean absolute error value also reflect reliable performance by SWOT in capturing real water level variations. In the second table, table number 2 represents the statistical analysis for Sukkur Barrage between SWOT and DIT water level. I have compared SWOT with DIT data for Sukkur Barrage only, since DIT was not available for the other two locations. In this plot, the statistical outcome are bit inferior compared to table number 1. These discrepancies are possibly due to varying reference surfaces, temporal resolution, and limited availability of only 6 DIT observations. Overall, these results demonstrate that SWOT provides accurate water level estimate and is well suited for hydrological applications in the Indus Basin. Now, conclusion. To conclude, this study validated SWOT-derived water surface elevation against in-situ data at Guddu, Sukkur, and Kotri, showing strong correlation with root mean square error values ranges between 0.55 to 0.8 meter. This highlights SWOT's potential for monitoring surface water, especially in data-scarce regions like Indus Basin. One of the limitations of SWOT is its lower temporal resolution, which is 21 days, but this can be addressed by combining data from multi-satellite missions. In countries like Pakistan, where installing and maintaining river gauges is difficult, multi-mission satellite data offer a practical alternative. Finally, for transboundary rivers, where data sharing is often restricted, satellite ultimately provide an independent and reliable source for monitoring river dynamics. So now, with the launch of SWOT, it is the time to say goodbye to the outdated river monitoring methods and welcome to the new cutting-edge technologies. These are the references which I have used in this research. Thank you very much for your attention.